Okay, in this video we're going to go through chapter 4, which focuses on exponential and logarithmic functions. So in this little graph I have here, I'll give you examples of each one. And I also give you this line right here. Now this line is y equals x. So that is telling you that exponential functions and log functions are reflections of each other across the line y equals x. So what does that remind you of? You should think for a second and you say, oh, yes, these two functions are inverses of one another, because inverses are reflections over the line y equals x. So notice a couple of other things. Y equals 2 to the x never crosses the x-axis, so that does not have any roots. Y equals log x never touches 0, or does it ever go negative for x values. So x can't be 0 and x can't be negative. So these are things that tie back to the functions and their graphs, and that will come up later on in the chapter as we try to, for example, solve equations. So let's get started on this chapter. Okay, so we start out in 4.1 with exponential functions. Now, we talked about growth and decay previously, so exponential functions can either be growing exponentially, so not linearly, but at greater than a line, and they can be decaying. So remember we tried to get the multipliers? So this is all tied together again. Look at our growth equation. Remember that the base of a growth equation is 1 plus the rate of growth, and that is expressed as a decimal. So they give it to you as a percentage, you turn it into a decimal, and you can get your base for growth. Decay is 1 minus the rate of decay. So clearly the base for decay is going to be less than 1, but still positive, and the base for growth will be greater than 1. And these are the resultant graphs. You can see growth is going up and decay is going down. Okay, on this slide, we're going to practice working with exponential functions. So the first thing you want to do is figure out what is your base. So this is an exponential function. I recognize it because the variable x is in the exponent location. Okay, that's what makes it an exponential function. Let's work with this a bit. First, what is the base? So the base is 8. The base is the number at the bottom. So we're going to evaluate the function for certain values of x. We're going to do this by hand just to get a feel for this. So here's your x and here's your y. Okay, so think about this. This is your x. These are your independent variables, and your y is a dependent variable. Okay, at one point in our problem set, I asked you to graph something, or actually determine the graph. So know that you have a stats part in your graphing calculator, and what you would do if you wanted to run a regression on this, you would put your x's in your L1 and your y's in your L2, and you would run a regression. So that's in stats. That will be in the problem set. So if you don't know how to do that, you probably need to contact me when you look at it as at the problem set. Okay, so that's a little aside. Let's continue what we're doing here. So since 2 is the exponent, 8 raised to the second power is 64. Okay, so I'm going to plot this as I go. So here's 2. And here's 64, say it's right about there. So what is this, by the way? Is this growth or decay? Well, your base is greater than 1, so you should say that it's definitely growth. Okay, let's keep going. Now look at this, 2/3. What does that mean? Well, that means that 8 is raised to the 2/3 power. Now that could be confusing for some of you, so let's break this down. This can be written 8, and then you take the cubed root of this squared term. So that's one way you can think of it. You can also think about it this way. you take the cube root and then you square it. That's going to be much easier. So this is why it's much easier. What's the cube root of 8? And you should be saying it's 2, because 2 times 2 times 2 is 8. So what is 2 squared? Well, that's just 4. So if I take 8 and I raise it to the 2/3 power, I get 4. So we're going to approximate this. So let's just say maybe that goes right about there. Okay, how about 0? Well, anything raised to the 0 power is always, forever and ever, 1. So if I have 0, I know that is going to be my y-intercept. So I'm going to put it down there. So we can kind of see the pattern already. Okay, how about if our power is -1? Well, what happens there, that turns into 1/8, right? Because 8 to the -1 is the same as 1/8 to the 1. Remember, negative just tells you that the location is not where it should be if it wants to be positive. So that location is technically in the numerator. If you move it down to the denominator, look what happens. It goes positive, and that gives you the fraction 1/8. Okay, how about this next one? Let's figure this out. Now, that's going to be hard for me to plot, so I'm not going to even really, it's someplace, below that. So I'm kind of putting it there, but you can see it's a little bit too close to approximate it. The reason why we're doing this is really to understand how to handle the powers and to get numbers for these exponents. So this is 8 to the -4/3. All right, so what is that? Well, that's the same as saying 1/8 to the 4/3. Okay, now we know that we can say 1 over the cubed root of 8, and then once we get the cubed root, then we're going to raise it to the 4th power. So the cubed root is 2, and 2 raised to the 4th power is 2 times 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So this is 1/16. So it's even someplace further down here. Okay, so your basic graph is going to be looking like this, the classic exponential growth. But hopefully, kind of playing around with these powers by hand gives you a good feel for how to get numbers and what these powers really mean. So let's go on to the next page. Okay, your book has a table that gives the law of exponents, but I like this one better. So I've added this to the slide. What I like about it is it gives you the law here, and it gives you an example here. So you want to definitely spend some time making sure that you are comfortable with these laws, because if you're not comfortable, it's going to end up making this section a little bit more difficult than it should be. Okay, they all seem to make sense when you look at them, but you really have to think about them to make sure that you kind of own them. Okay, we talked about fractional exponents a second ago. Here is the reinforcement of that. Okay, I'm going to go one more step with this because I just did this with you and it's important. So remember, that means the same thing. Okay, see, they did it for you down here, but I just walked you through it right there. So that's important because a lot of times it's easier to work with it this way. So one advantage of being very comfortable with exponent rules and with bases and with converting bases is that it makes it easier to solve some problems algebraically. Okay, so given a problem like this, 8 to the third equals 2 to the x. There are many ways you can do it. You can take the log of both sides. You can go all kinds of crazy ways, and they all are correct. But a very nice and easy and neat way to do it is to do the following. Look at your two bases and say, okay, the 2 is the smaller of the two bases. Could I get 8 to be base 2? And we've just used 8, so you should say yes. 8 is really 2 to the third. Okay, so we have written 2 to the third, because that's what x is, but then that is raised to the third power. And that's going to be power to power, so you're going to multiply those. So keep that in mind for just a second. Okay, so that's my setup. So let's do the power to power. So 3 times 3 is 9. So this is 2 to the 9th equals 2 to the x. So what are you noticing? For this expression, or for this equation to be true, since they have the exact same unique base, the only way it's going to be true is if your exponents are equal. So therefore 9 has to equal x, and we are done. So let's try doing the same thing for this next problem. So it says 25x, and you can probably guess where I'm going with this, equals 5 to the 8th. Okay, so your 25 also can be written as 5 squared. So this is 5 squared taken to the x power, and that equals 5 to the 8. Okay, so this is power to power. You're going to multiply it. Again, you want to go back over those exponent rules if that's not a comfortable rule for you. So this is 5 to the 2x, and that has to equal 5 to the 8th. So 2x equals 8, and x equals 4. All right, so that is called unique base, and it's a nice way to solve. You should always kind of see if you can solve things that way before you do a whole lot of other work. Okay, we're going to go to natural exponential functions next, which is how 4.2 starts. Okay, in 4.2, the authors begin to talk about the natural exponential function. So the natural exponential function is the most important of all. So that's base E, and base E is easy to work with and can be used to model many scenarios. Okay, and we'll talk about some of those scenarios in this video. To calculate the instantaneous rate of change, the slope that is, of the natural log function, you simply evaluate it at that x value. So that's kind of a nice little feature. And we're not going to do a whole lot with this, so I'm just making these statements. The slope of e to the x when x is 0 is the value of e to the x evaluated at x is 0. Okay, so this only occurs with exponential functions of base e. So just know that e is very special. Okay, we'll go on to the next slide. Oh, and this should have said is, and I'll change that on your copy. Okay, in 4.3, they talk about the logarithmic functions, and remember, logarithmic functions are simply the inverse of exponential functions. So as inverses, therefore, the logarithmic functions are the reflection of the exponential functions across the y equals x. So we talked about that on the first page of the slides, when I said that those two functions are reflections of each other across the line y equals x. Okay, in terms of scaling, the reason why we do logarithmic functions is because it makes it easier to work with large numbers. So on page 171, they draw our attention and they say, look at the horizontal scaling of the x-axis on this page. So what's happening is these numbers are going up very quickly. One would say exponentially. Okay, this advances powers by tens, which is very different from the scales we have used previously. So in the textbook, they give you this information and they ask you to kind of fill it in. So I filled it in on this row. So notice how, even though the numbers initially were fractions, they are all base 10. So I wrote them in as base 10, and that is the scale. So it's consistent in terms of you're increasing by increments of base 10, but the spacing in between are not the same numbers. So this is kind of a different thing for us. So that's just something I wanted to point out because it's kind of the part of the beauty of log functions. Okay, so here's a little reinforcement about what I said on the first page, and then I referred to just previously. So the family of log functions, exponential functions and log functions are 1-to-1. What does that mean? 1-to-1 means that they are functions and the inverse are also functions. That's what the 1-to-1 property is, and we had discussed this in the previous chapter. Notice some fundamental characteristics of these exponential and then log functions. with exponential functions, y can never be negative. So which one is the exponential function? So the exponential function is this one because the x is the exponent. And notice your y value is never going to go below the x-axis. In fact, it's never even going to hit the x-axis. So it can never be negative, and it can never be 0 because it's asymptotic. That's a nice word to know. It's asymptotic to the x-axis. Okay, so now look at the log function. Y equals log base 2 of x. It's the inverse because you can see that it's a reflection over the line y equals x. And it is asymptotic to the y-axis. Do you see that? It kind of makes sense when you think of them as reflections of each other. So you can never take the log of a negative number or of 0. Okay? And that's because of this relationship. So get comfortable with that. Okay, there are some equation-based implications of the fact that exponential functions never equal 0. So if you are looking for the roots of an equation such as this, the only root you're going to have is x equals 7 because this exponential piece will never go to 0. So let's look at another one. So let's say I have this function and I want to figure out what the roots are. So I already have this factored out. I'm going to leave that there. And this is going to be, let's see, x minus 7, x plus 1. If you factor it, that's what you get. Okay, so if this is going to equal 0, it's going to equal 0 where the factors are equal to 0. So this factor is equal to 0 when x is negative 1. This factor is equal to 0 when x is equal to 7. So now look over here. This has an x in it. In fact, it has an x 2 places, so it's definitely a factor. When is that factor equal to 0? It's only equal to 0 when this part goes to 0 because I know this part will never go to 0. So this factor is going to get us x equals 0. So those are my 3 factors. Those are the 3 places that this function right here, will cross the x-axis. Okay, so the implication of the exponential function never equaling to 0 means that this is not going to help us find a root. Okay, it can't go to 0. Okay, one thing that's very, very important is you have to be completely comfortable writing logs or logarithmic functions as exponential functions. So there's a way to do this. This phrase, logs equal exponents, is always a good one for me. Looking at this is our first example. I see this is written in log form. How do I write it in exponential form? The first thing I say is, what's my base? This is your base, 16. 16 is my base. Logs equal exponents. Logs equal exponents. That's my exponent. Then that equals 2. So this is how you write log form in exponential form. And you can see that those are equivalent. You can either write it in log form or in exponential form. Sometimes when you're trying to solve for x, one form will be superior to the other, and so you have to be able to go back and forth. Okay, let's practice this next one. Because I have a log here, it's in log form. What's your base? Your base is this 2. Okay, logs equal exponents. That is 2's exponent. And then this equals 1/4. And do you see why? Because what's this? Isn't this really 1 over 2 squared? And isn't 1 over 2 squared 4? So that's 1/4, and that makes sense. Okay, think about this. This is the 4th root of 16. Isn't it true that 2 times 2 times 2 times 2 is 16? So therefore, that substantiates the fact that 2 is indeed the 4th root. All right? So hopefully you'll get comfortable doing this, but practice is your best way to get that level of comfort. And with the idea of practice in mind, we're going to practice writing exponential functions as logs. Okay, the second you see you have an exponent, you know you have an exponential function. So think two things. Logs equal exponents, and what is my base? Okay, so what's your base here? This is your base, it's 2. So the log of 2, okay, logs equal exponents. What's the exponent? X. And the 16 goes in the other spot. Okay, so logs equal exponents, and then figuring out what your base is. Okay, let's do the second one. What's your base? Your base is log 10. Okay, now with log 10, you don't usually put a 10. Okay, the 10 is implied if you have just the word log. Okay, so I can just write log. Okay, logs equal exponents. What was the exponent? It was 3, so then the x goes behind here. Okay, so make sure that this makes sense to you. You need to be able to go back and forth. So can you go forward from here? This is in log form. Can I get that exponential form back? What's your base? Your base is 2. Logs equal exponents. What's the exponent? X. And then that equals 16. Those match. Let's do the next one. I don't see a base. My base must be 10. Logs equal exponents. What's your exponent? 3. And this equals x. Okay? So be able to go back and forth from one form to the other form. Okay, change of base formula is an important thing to note, and your textbook goes over it. So our calculators easily work in base 10 and base E. Those are the two that all the calculators have. Many calculators can now also work in other bases, but the change of base formula comes in handy if your calculator does not work in other bases or if you just want to be able to convert. So this is how the change of base formula works. If you have the log of any kind of base and you have an n here, you can convert this to base 10 or to ln, which is base e. And all you're going to do is you're going to write log 10, and then the top number, or the bigger number, is the numerator. The base is the bottom. The bigger is the numerator. The base is the bottom. Either way, put it in your calculator, and you will get a number, because your calculators can work in base 10 and in base E. So let's practice. Here is an expression. It's in base 7. I want to use change of base formula to put it into base 10. So this is how I do it. I look at that and I say the bigger number goes in the numerator and the little number goes in the base. So I can either write it like that, or I can say I can use natural log. In any case, you'll get the same answer. So let's go ahead. We'll put that in our graphing calculator. So it's just a fraction. So natural log of 20, close your parens, divided by natural log of 7, close your parens, equal. So if I were to round it to the nearest hundredth, I would get 1.54. So just check to make sure that you can do that with your calculator. Okay, here's another one. You can stop the tape and then turn it back on and see if your answer matches my answer, or you can just listen through it. Okay, looking at this, I know I can change it into base 10 by saying log 17 over log 3. Or I can say natural log 17 over natural log 3. I'm now going to put that in my graphing calculator. So natural log of 17, close my parens, divided by natural log of 3, close my parens, and I'm getting, if I round it to the nearest hundredth, 2.58. So this is 2.58. Okay, change your base. Know how to do that. Okay, so now we're going to focus on natural log, which is ln. Natural log, excuse me, has a base, is your e. Okay, so you want to be comfortable knowing that that's a relationship. So we're going to rewrite this. This will say natural log on your copy. We're going to rewrite it in natural log form. So how do we do that? If I see I have base e, I say natural log. Okay, logs equal exponents. So what is my exponent? My exponent is negative 1/2. And this number goes behind. Okay, so that's rewriting it in exponential form. Let's do the same thing, rewriting it in natural log form. Let's do the same thing here. Okay, I want to write it in natural log form. I see my base is e, so I'm going to say natural log. Logs equal exponents. What's my exponent? It's 0, and the 1 goes here. So now I know that the natural log of 1 is 0, and you can check that with your calculator if you want, and you'll find that that's exactly the case. You can also check, is the natural log of 1 over radical e equal to negative 1/2? And it is. And another thing we can talk about, can't I write this that way? And that equals negative 1/2. So that's also a true statement. Okay, so there's lots of math going on here. That's a good final answer. This is a good final answer. Okay, now we're going to take something that's in natural log form, and we're going to write it in exponential form. So since it says natural log, I know my base is e. So I write down the e. Okay, logs equal exponents. That's my exponent. Okay, and that's going to equal 1 over e squared. Now, isn't that a true statement? Isn't this in the denominator the same as bringing it up with a negative 2? Of course it is. So that's why that statement is true. Okay, look at this last one. Your base, you know it's natural log, so therefore you know your base is e. Write down the e. Logs equal exponents. That's your exponent, and that's going to equal whatever was behind the natural log. Okay, isn't that true? Can't I write anything to the first power and have it be itself? So yes, that's true as well. So sometimes when you rewrite the form, you will see the relationship a lot clearer. Also, if you're trying to solve for an x, sometimes just rewriting the form will allow you to quickly solve for that x. So let's keep going. Okay, before we get into talking about logarithmic transformations, just like you have transformations to other functions, we're going to first go through some of the logarithmic rules or properties. Either way is fine. Okay, if you have this, so this is log base a of this product, the rules of logs tell us that you can break up a product into addition. So multiplications behind the log term can be written as additions. Okay, so you can expand it into an addition. So that is an important rule to know. So that's the first rule. Second rule in this situation is the power rule. So if you have behind the log term a variable raised to a power, you can bring that power down in front and write it like this. This is called the power rule. All these rules come in handy when you're trying to do math with log terms. Now you have another important one. This is a division. The division is written after the log term. All the divisions become subtractions. Okay, so that's key. Okay, so now this is interesting. Log base a of 1 equals 0. What does that mean? Well, it's hard for me to understand this, but what I can understand is if I write it in exponential form. What's my base? A, logs equal exponents. That's 0, and that's going to equal 1. So that is telling me, once I change the form, any number raised to the power, to the 0 power, is always going to be a 1. So I didn't recognize it in this form, but I do recognize it in that form. So that's an example of how changing the form sometimes can reveal information that you didn't see in the previous form. Okay, on this slide, we're going to be using these properties of logs that we just went over. So if they ask you to write this using the property of logs, and they want you to write it as one term, you're going to kind of undo the property. So I see I have an addition, and I see my log term is natural log. So I'm going to write natural log, and I know that every addition previously was a multiplication. So that's my first step. That's my second step. That's my best answer. Okay, look at this next one. I see that I have an addition and I have a subtraction. Whatever's being subtracted goes in the denominator. Whatever's being added goes in the numerator. And then the natural log goes in front. So I have that, but what can I do with that? Well, I can do several things. Look what happens. And this is why undoing these properties sometimes makes numbers easier to work with. So 3 goes into itself one time. 3 goes into 12 4 times. 4 goes into itself one time. 4 goes into 16 4 times. This whole expression can be simplified to natural log of 4. And that was just by using my properties. Okay, here's one more. Whenever I see a number in front, I always will do the power property first. Then look at your operations. So I see I have x on top. I see I'm going to have an x cubed because of the power property on the bottom, and another x squared on top because that's an addition. And natural log is written in front. So look what I have here. X times x squared is x cubed. So this is natural log of x cubed over natural log of x cubed. Oops, sorry, I didn't want to write that. So let me rephrase that. This is natural log of x cubed over x cubed. Well, what's x cubed over x cubed? That's just 1. So natural log of 1. And what did we just learn? Natural log of 1 equals 0. So by using the properties or undoing the expansion of the properties, I can make for much easier math. Okay, it's clearly much easier to work with 0 than to work with that. Okay, it's clearly much easier to work with natural log of 4 than to work with this. Okay, and it's probably even easier to work with natural log of 12x than to work with what you have there. Okay, so good things to know. More work ahead of us. Okay, so now we're at the point that we want to talk about a little tiny bit about transformations using law of exponents. So think about this. If we have y equals natural log of 8x, can't we make every multiplication is an addition? So I have this. Now, what do I know? This is a parent function right here, natural log of x. And what's happening to the parent function? You are increasing it by natural log of 8. So you are taking that parent function and you are shifting it up vertically. So what am I doing? What kind of transformation is this? It's a vertical shift up. By what? By natural log of 8. Okay, so you can also get some insights about transformations by using your properties. Okay, so here are some important identities. And again, you can see these. You can see that they're true if you can just rewrite it in another form. So if it's in log form, we're going to rewrite it in what? In exponential form. What's your base? You should be saying A. Logs equal exponents equals this. So can't we see that's the case? But it's revealed to us when we change form. How about this next one? This is in exponential form because a base is raised to a power. So even though you have a log in the power, it's still considered exponential form. So we're going to rewrite it in log form. So what's your base? Your base is A. logs equal exponents. What's your exponent? Log a of x, and then the x goes here. Doesn't that make perfect sense that those two are equivalent? So what can we say? What we're seeing here is that if we have log a next to the base, it ends up being the same. You can say that that's x because this holds, but you can see why that is the case. So look over here. You have a next to log a, and what does that equal? Well, that equals the x. So they're just identities that you can play around with that jump out at you when you change the form. Okay, so we're not going to do a whole lot with compounding interest formulas, but it's an important thing to stop and think about this for a second. And how is this related to exponential growth? If you want to figure out how much an investment that's continuously compounding is going to be worth in the future, this is what you want to find out. You want to find out how much money you're going to be getting in the future, right? So here's your initial investment. Just like initial population, we did that when we were doing exponential functions previously. So that's your initial investment. Here's your base. Base E, remember I told you base E is very important. It comes in very handy. And here is your exponent. So this is indeed an exponential function, and it's used in the banking business. And it's a wonderful thing to know how important base E is and how much you use it without even realizing it. So you can figure out if you knew what your interest rate was, that's the R, you knew how long you're going to keep the money in the bank, and you know your initial investment, you can figure out how much your investment is worth in the future. Okay, so here's another little mini topic that we're not going to do a whole lot with, but it's a nice application of logs that occurs in biology. So logistic growth. Logistic growth takes into account the carrying capacity of the environment. So that means that you're not going to get a continuous growth curve. You're going to really have something that levels off and approaches a certain number. So here is an example of that pattern, and the carrying capacity ends up being the numerator. And I believe I have another picture for you on the next slide, so we'll go to that. And this is how we're going to finish up. So there's lots of good things. The big takeaway is this: you can do a whole lot with logs. And they occur places that you don't even think about. You know, the banking industry, this is growth of populations, growth of viruses, growth of really anything. So let's go to the next picture and I'll show you the curve. Okay, there it is. Okay, so here is our logistic growth curve. So you can see that you do indeed have an exponential growth pattern initially. Okay, so you're growing exponentially, but then over here what's happening is you level out. And how come you're leveling out? Well, you're leveling out because the environment is putting a lid on how much things can grow. So we can see that the environment, whatever this happens to be, the carrying capacity is 1,000 whatevers, whatever the units are. So where is this curve the steepest? Well, it's steepest right in here. And it's also the place where, and we haven't discussed this in this course, but for those of you that have taken calculus, that is the inflection point where it's the steepest. Your function is concave up. So it's concave up here, and it's concave down here. So although exponential growth does occur in nature, quite frequently you will have more of a logistic curve where you have a tapering off. The tapering off occurs at the carrying capacity. And then you can repeat this pattern over and over again. The population gets wiped out, it's going to start growing exponentially until it gets to the carrying capacity. Okay, well that's the end of this PowerPoint, and you should be able to do the problem set that goes along with this chapter now.